Welcome to lecture number 15 for ECE 321, Analog Electronics. In this lecture, we're going to look at the common base and common collector amplifier. Now, a little bit of review. Where we're at. In the previous lectures, we looked at creating this circuit. This is a transistor where I'm going to have RC convert the collector current into a voltage. RE is chosen to help you stabilize the Q point. R1 and R2 are chosen to set the Q point at VC equals 6 volts. IC is 6 milliamps. I've added capacitors to the base, collector, and emitter to isolate the circuit at DC. We're now going to look at how to set this up as a common base or common collector amplifier. So first thing you need to do is you need to replace the diode with the small signal model. That would be a resistor. And from before, the resistance is 867 ohms. That's your NVT over the base current at DC. And also note that the 12 volt source, this is 12 volts DC plus 0 volts AC. We are doing AC analysis right now, the small signal model, so this looks like 0 volts. And I now want to analyze what's the circuit look like as I go from the input to the output. So what I would do when I draw this, let's start from the input right here. At the input, that takes you to the emitter. The emitter goes to ground through RE. Emitter then goes to base, which is tied to ground through RF. Emitter goes to collector through your beta IB. And this was the base. Here's the collector. Collector goes to ground through RC. And here's ground. And there's your V out. So that's your small signal model. It helps to redraw the circuit. And that's what you should get. I now want to find the two-port model. So for the two-port model, I'm going to go through 4 tests to find RN, AI, ROut, AOut. For the first of those parameters, let's find RN. Again, I don't really know what to do with that current source, so what I'm going to do is apply a 1 volt test voltage and see how much current I draw. If this is 1 volt, this current is 1 over 100. This current is 1 over 867. This current is 200 times current through the base. So this will be 200 times 1 over 867. So that's the total current. And if you notice, this is actually the equation for 3 resistors in parallel. The resistance will be 1 over that. So this is actually RE in parallel with RF in parallel with a fictitious resistor that looks like RF over beta. That's this current source does that. So if I plug in numbers, what I get is 4.13 ohms. So that's the input impedance. To find the input gain, apply 1 volt at the output and see what the voltage is at the input. And here I can guess the answer. If this is 0 volts, I've got 0 for current plus 0 plus 200 times 0 equals 0. That balances. So that's the voltage at the input. AI equals 0. To find the output impedance, I'll short the input, find the impedance at the output, and again it's not obvious. So let's apply 1 volt at the output. If this is 0, IB is 0, 200 IB is 0, all I see is 1000 ohms. So the current I'm going to draw is 1 milliamp. The resistance then is 1 volt over 1 milliamp, 1000 ohms. And the last parameter to find AOut, apply 1 volt at the input. This current is 1 volt over 867. This current is 200 times that. 200 over 867. The voltage then is I times R. So this voltage will be RC times beta over RF with a plus sign. We're plugging numbers. A out is 230. So putting it all together, the two-port model for the common base amplifier looks like this. It's similar to the common emitter amplifier. The common emitter amplifier had a gain of minus 230. This has a gain of plus 230. It's got the same output impedance. What's nice about it is it has a low input impedance. The common emitter amplifier is used if I need a low input impedance, and that would be typically like if I have a phonograph needle or something where the signal is a current. I don't want to block the current, I want to allow it to flow. That's what this does. This has low impedance for current, it lets current flow. Okay, so what you do with a common base amplifier. Suppose I were to cascade them. Well, if I have two common base amplifiers, here's my first one, here's my second one. Find the two-port model. And kind of obviously looking in, the input impedance will be 4.13 ohms, AI equals 0. To find the gain, apply 1 volt at the input. If this is 1 volt, this is 230 volts. By voltage division, this is 4 over 1000 plus 4 times 230, 0.94 volts, times 230 gives you 217. So that's the gain of two stages amplified 217. And the output impedance, if this is 0, this is 0, this is 0, that's 0, output impedance is 1K. So if I cascade two common base amplifiers, what I wind up with is this. The output impedance is 1K, input impedance is 4.13, and the gain is right here, 217 VN. And kind of notice that two common base amplifiers cascaded are actually worse than a single common base amplifier. It basically does nothing to cascade common base amplifiers. That's not what they're for. I could verify that in CircuitLab. If I build a common base amplifier in CircuitLab, so here's kind of the heart of it. The base is tied to ground. That makes it common base. Here's my input. Apply a 1 millivolt, 1 kilohertz sine wave at the input. Measure the voltage at the output, where this is large, like 10 mega ohms. And the output voltage is 200 millivolts. So that says the gain is 200 versus 230 that I calculated. To find the input impedance, what I'll do is I'll add a resistor in series. If I make this 4 ohms, kind of cheating because I calculated, I know what the input impedance should be, 4 ohms. The output should drop in half. Make that 4 ohms, and now the voltage at the output is 108 millivolts. What that tells you is, here's your input. Here's the 4 ohms that I added. Here's the Rn that I'm trying to calculate. By voltage division, the voltage at this point will be your Rn over Rn plus 4 times 200 millivolts. That's what the gain would be without that resistance. Produces a gain of 108. So solving backwards, I get the input impedance is 4.7 ohms. Similar to what I calculated. A little bit different, but similar. To find the output impedance, can make this 0 ohms, make this 1 millivolt. And now take the load, make that 1 kilo ohms. And what happens is, from the two-port model, I have my output impedance. I now have 1 kilo ohm load on it. By voltage division, the voltage here will drop as 1K over R out plus 1K times the input voltage. Well, I know the input voltage. With no loading, it was 209 millivolts. With loading, it's 104 millivolts. Solve for R out. And what you get is R out is 1016 ohms. Getting close to what we calculated. So putting it all together, this is the common base amplifier that we calculated. This is the common base model that we found experimentally. The reason we're different is primarily that the beta, the transistor gain that CircuitLab uses, is about 150. We're assuming 200. Beta is somewhere between 100 and 300 for a 3904 transistor, so either one is possible, is valid. If you built it, you're going to get a third answer, because again, it'll be somewhere between 100 and 300 for the gain. So likewise, you're going to get three answers: the one they calculate, the one you find experimentally, and the one from CircuitLab. As I mentioned, common base amplifiers are not really designed to be cascaded. What they're for is the very first stage. If I have a multi-stage amplifier and the first stage needs to have a low input impedance, that's a common base amplifier. If, on the other hand, I can tolerate a high input impedance, I'd probably use a common emitter amplifier. So that would be common base. The second one to look at is a common collector amplifier. With common collector, I take the collector and tie it to ground, and I can either do it to earth ground or 12 volts, because again, this is for the AC signal. This 12 volts is 12 plus 0 sine omega t. So the AC voltage is 0 up here. Ground is also 0. Pick your favorite, doesn't really matter. Connect this either to power or ground as long as it's a constant. The AC part doesn't have any ripple. That'd be for the common collector. Now the input goes in at the base, output goes at the emitter. What's the corresponding two-port model? Well, again, the first step, let's do it this way, is to replace this with its small signal model. That'll be RF. And over here is your beta IB. Now at the input, I'll go from the input. First thing I see is R2 to ground. I see R1 to ground. Takes you to the base. At the base, I have RF going to the emitter. And the emitter goes to collector, which is tied to ground, through beta IB. Oops, misspelled 200. And here's your output. So again, the first step you do is redraw the circuit, get your small signal model. Now, find the two-port model. So the two-port model, let's start with Rn. To find Rn, I'll set the output to 0, find the impedance looking in, and what I see is R1 to ground, R2 to ground, and RF to ground. So the input impedance is just R1 in parallel with R2 in parallel with RF. Plugging in numbers, Rn is 605 ohms. To find AI, I'll apply 1 volt at the output. So these don't really matter. These are kind of shorted with 1 volt. So this is 1 volt at this point. I now have a voltage divider. That'll be R1 in parallel with R2, and RF as a voltage divider, which gives you R1 in parallel with R2 over that plus RF. That's the gain from the output to the input. This is the circuit where we have AN is not equal to 0. To find the output impedance, short the input, find the impedance at the output. Again, that's not really obvious, so let's apply 1 volt at the output and see what you get. If I have 1 volt here, the current will be 1 volt over RF plus 200 times 1 volt over RF. Kind of one thing you can do, if I could change the sign of IB, change the sign of this one, I've got a double negative, that works. So this current is 1 over RF plus 200 times 1 over RF plus 1 over 100. That's the total current. The impedance then is 1 volt over the current, or 1 over that. And if you notice, this is the equation for 3 resistors in parallel. This is RF in parallel with RE, in parallel with a fictitious resistor, RF over beta. Solving, that gives you 4.14 ohms as the output impedance. And the output gain, apply 1 volt at the input and see what you get. So this is 1 volt. I'm not sure what to do. So let's do a voltage node. At this point, the current's set to 0. So that current plus this current equals 0. That's V out minus 1 over RF plus, I'm going to throw in a double negative here, 200 times V out minus V1 over RF plus V out over RE equals 0. Solving for V out, I get this. It's actually a voltage divider. Yeah, something like that. Gives you this equation. V out is 0.9568 volts. So the net result is this. Here's my input impedance, output impedance. This is non-zero. This is the one amplifier that's not zero. And here's the output gain. What's special about the common collector amplifier is this has a low output impedance. If I ever want to have a low output impedance, that'd be the common collector. That's useful for doing things like driving an 8-ohm speaker. In CircuitLab, I can check my answer. Take the circuit, connect it up as a common collector amplifier, so the collector is tied to ground through a capacitor. Now find the gain from the input to the output. First, to find A out, let's make this a 1 millivolt, 1 kilohertz sine wave. Measure the output voltage, and the output voltage is 0.956 millivolts peak. That's A out. To find R out, let's see, where am I at? To find R out, connect VN to 0. Okay. Okay, so Vn goes to 0. Apply 1 kilohertz sine wave at V out and measure the current. In CircuitLab, I can actually measure the current. That's another way to do it. The current is 227 microamps. So the resistance is 1 millivolt. That's this guy, 1 millivolt. 1 millivolt produces 227 microamps. Take the ratio, I get 4.41 ohms. It's supposed to be 4.14. To find the input gain, apply 1 millivolt. No. Set V out to 1 millivolt. Okay. Set the output to 1 millivolt. Make the input 10 mega ohms, something large. Measure the input voltage. And from CircuitLab, I'm going to get 736 microvolts. So the gain is output over input. That over 1 millivolt gives a gain of 0.736. And to find the input impedance, okay, I use the current measurement. Make this 1 millivolt, and then measure the current. In CircuitLab, I can do that. So 1 millivolt in produces a current of 1.9 microamps. The ratio is the gain. Also set V out to 0, right here. Gives input impedance of 508 ohms. Again, reasonably close to what I calculated. So here's your two-port model. Again, what I calculated versus what I measured. One thing to note, a lot of students will try to memorize these circuits. Part of my job as an instructor is to see that if you're trying to memorize and you're not learning the concepts, you won't pass the quizzes. So a lot of times what I'll do is I'll change the circuit. If you're doing the procedures that we kind of followed here, it's not a problem. If you're trying to memorize, you're stuck. So what I might do is, given this circuit, go back one. Okay, where are we? I'm lost. There we are. Given this circuit, let's change it slightly. Again, so if you've memorized this one and I change it, you're kind of stuck. Part of my goal as an instructor is to see that you can't memorize your way through electrical computer engineering. There's just too many circuits to memorize. The techniques and concepts always work, but the circuits might change. So what I might do is say, okay, here's a circuit. Suppose I add a 1K resistor right here. What's the small signal model? Again, the equations don't work anymore because it's a different circuit. Or let's add a 1K resistor at this point. Now what happens? Again, so if you're going through the procedure, it'll be the same as before. I'm going to go from the input to the output. And let's erase all this. It's not that bad if you kind of learn the techniques. Going from the input, I now see a 1K resistor, and that takes me to the base. Base goes to ground through R2. Base goes to ground through R1. And I now go to the emitter through RE. Emitter goes to collector through beta IB. Here's IB, goes base to emitter. And now the collector goes to ground through a 1K and a second 1K. So again, that's kind of what you can expect on the quizzes and tests. I'm going to take these circuits and modify them. What I'm doing is if you memorize the equations, you're kind of sunk. If, on the other hand, you just learn the techniques, how to draw the small signal model, you're okay. When I give you this circuit and ask you to find the two-port parameters, again, this one, there's the equation in the lecture notes. That one you know what to do. Suppose I were to modify it slightly. Have a resistor in series. Yeah, kind of like that. Make that a 1K. Now what's the two-port model? Again, same procedures as before. Equations will be different, but same procedures. What I'm testing on is the procedures. Can you solve this type of circuit? I'm not trying to test on memorization. So anyway, that's the common base, common collector amplifier. So right now we've got a shopping list. I have a common emitter amplifier from the previous lecture. I've got the common base amplifier and common collector. What they're good for is the common emitter amplifier is your bread and butter amplifier. It's got a fairly high input impedance, fairly high output impedance, and a high gain. The common base amplifier could be used on the first stage. If I want to have a low input impedance, I'll use the common base, otherwise use common emitter. The common collector has the low output impedance. If I want to have a low output impedance, the last stage will be common collector. If I don't care, I'll use the common emitter. And these are kind of like the Legos, the building blocks you have to build a multi-stage amplifier. And that we'll look at in our next lecture. So that's lecture number 15, Common Base, Common Collector Amplifier.